So we'll move on to our final talk of the session from Harriet Turner. Oh, it has moved on too fast. No spoilers. She has recently started I said no spoilers. It's all right. She has recently started a new position at the Met Office as a space weather scientist. And before that, she was at Reading University studying space weather and all kinds of techniques that I think she will mention in this talk. So I'll hand it over to her to actually hear about what I think we most often think of when we talk about resilience in space, which is resilience against space weather.
Well, it clearly doesn't want to show my title slide, but thank you for the introduction and thank you for the invitation to talk today. Yeah, so I might as well get started as it's not going to show my title slide. So the Met Office describes space weather as the changing environmental conditions in near-Earth space. And this is driven by the variability and the dynamic nature of the sun, which influences the entire solar system. Interactions of the sun's magnetic field and the plasma with the Earth's magnetic field causes a variety of impacts, affecting modern technology and power grids and also human health for those in space and on high altitude flights. Severe space weather is in the UK National Risk Register as it could have significant impacts on technology. For society to be resilient to the effects of space weather, the risk needs to be appropriately acknowledged and the local and wider scale impacts understood through modelling reasonable worst case scenarios, as well as the more moderate space weather events. We also need robust and accurate forecasting methods, which will help to increase the warning time we have for events, and therefore allow us to put in place mitigating actions. So in this talk, I'll go through some of the basic drivers behind space weather, what impacts these may cause, and their associated mitigation. But I'll also talk about how space weather is currently forecasted and how my work through using data assimilation can be used to improve these forecasts. So the solar wind is a constant stream of charged particles that flows off the sun, and this fills the whole solar system. It's comprised mostly of protons and electrons, and as it flows off the sun, it drags with it the sun's magnetic field. Due to the rotation of the sun, the solar wind forms an Archimedean spiral shape. Sectors of fast or slow solar wind, which might rotate for several solar rotations, are formed, such as in this diagram here. Where slow solar wind catches up with fast solar wind, stream interaction regions form, and these are regions of enhanced solar wind density and magnetic field. These can be a source of moderate space weather, and if they persist for several solar rotations, they can be a source of recurring space weather. Coronal mass ejections, or CMEs, are large eruptions of plasma and magnetic field, and these can travel at up to 1,000 kilometers per second. They propagate through the solar wind, so the background conditions can affect their speed and arrival time if they are directed towards Earth. They are the main driver of severe space weather, and certain factors will make a CME more or less likely to cause an impact on Earth, such as their speed and the direction of their magnetic field. So space weather can cause a number of impacts, particularly on modern technology. So it can impact spacecraft, affect the health of humans in space or on high altitude flights, affect the power grid, and also cause brighter aurora. So I'll now go through a few of these and the possible steps that can be taken to mitigate those impacts. So due to electrons in the space environment, charging of a spacecraft can occur. Lower energy electrons can differentially deposit charge across a spacecraft, which can then discharge and damage electronics and solar panels. High energy electrons can embed themselves in the insulating material between components, and when they discharge, the insulating material can be damaged. And this can cause failures in components, which can lead to the whole spacecraft no longer functioning. Single event upsets can occur due to the deposition of charge in sensitive microelectronics, either through direct ionization or through nuclear interactions. Interaction with particles and radiation can lead to premature aging and degradation of a spacecraft, meaning that it might not survive its planned lifetime. So during a space weather event, currents in the upper atmosphere can heat it and lead to its expansion. And this can then encapsulate a spacecraft that wouldn't normally be in the upper atmosphere, leading to increased drag on the spacecraft and possible orbit degradation. And this did happen to a Starlink launch a few years ago. Spacecraft can be hardened to the effects of damaging radiation through the use of specialist materials and through shielding. However, this is very mission dependent. Increasing the radiation hardening on a spacecraft will significantly increase the weight of it. And this means that more fuel will be needed for launch and to maintain orbit, which adds cost to the mission. Spacecraft can be switched off during space weather events to allow charge to diffuse, meaning that there won't be any damaging discharges, but this can also lead to economic impacts through the outage of that spacecraft whilst it's turned off. If certain systems are shut down or damaged during a space weather event, backup plans can be put into place to use different systems that are not affected. For example, that there are protocols in place for when aeroplanes lose GPS. Humans on the surface are mostly protected by the Earth's magnetic field. However, radiation can affect those who are in space and on high altitude flights. So this can be through electromagnetic radiation or energetic particles. And these can damage or destroy living cells or damage or alter DNA. This can lead to a reduction in white blood cells and so impacts the immune system, cause nausea, hair loss, cancer, and extreme cases death. So not very cheery, unfortunately. But to mitigate against the effects of radiation, the routes that aircrew fly on are heavily regulated. So polar regions experience high levels of radiation as the Earth's magnetic field is directed such that it funnels particles down towards the Earth rather than deflecting them. So crew are only allowed on a certain number of transpolar flights and on high altitude flights to limit their exposure to harmful radiation. During space weather events, transpolar flights may be rerouted to avoid the more dangerous regions. And astronauts on the International Space Station are heavily monitored for their radiation dose. And during space weather events, they can shield in regions of the spacecraft that offer high levels of protection. Disruption in the Earth's magnetic field from space weather can induce currents at the surface, known as geomagnetically induced currents, or GICs. Magnetic effects from GICs can overload transformers, causing them to shut down. They can be damaged, and in worst cases, they can fail completely. So this can lead to blackouts either on a local scale or more nationally in the case of a severe event. So a commonly used example of this was in 1989 at the Hydro-Quebec power station in Canada, where a space weather event took out a transformer. And I think that might be a photo of the transformer, leaving a 9-hour blackout for thousands of homes and $13.2 million in damage. So maintenance of power lines can be scheduled around the solar cycle. So during solar maximum, CMEs are more frequent. And so increasing maintenance around this time can help protect against an increase in damage. Parts of the power network that are vulnerable can be disconnected in times of space weather to avoid them being damaged. And there is research into using capacitors, which can be used to block GICs in the system. But it's not all bad. The aurora are caused by precipitating particles colliding with native atmospheric species, causing them to glow. They are a visual representation of the energy transferred from the solar wind into the Earth system, and they are enhanced and visible at lower latitude during an intense space weather event. So in May of last year, several large Earth-directed CMEs caused a geomagnetic storm, and that made the aurora visible over much of the UK. And I actually took that photo down on Dartmoor, so that shows just how low latitude you could see the aurora at. So to forecast space weather, the current mechanism uses a coupled modeling system. So it's initialized using observations of the photospheric magnetic field, which is the magnetic field on the surface of the sun. And this acts as the inner boundary condition to a coronal model, which models the sun's outer atmosphere. The output from the coronal model then feeds into a solar wind model, which propagates the solar wind out from close to the sun into the solar system, so out to Earth or beyond. It is more efficient to split the space between the sun and the Earth up in this way, as they are in different regimes. So the corona is more magnetically dominated, whereas the solar wind is more flow dominated, and so it is more efficient to have a tailored model for each regime. Data assimilation, or DA, is a technique that combines model output with observations to form an optimum estimation of reality. It's led to large forecast improvements in terrestrial weather forecasting, but it has been underused in space weather forecasting, and particularly in the solar wind. So this is where my work has come in. So the Berger radius variational data assimilation, or BRAVDA scheme, is a model that was developed at the University of Reading. It uses observations of solar wind speed from spacecraft at a similar orbital distance to Earth and at a similar latitude. So this is combined with information from a coronal model to provide a new inner boundary condition for the solar wind model that has been updated with information from the observations. The model works by taking an observation, so for example, at the red cross in the first panel, and mapping this backwards in time to the inner boundary, as it contains information about the solar wind state at that time. So that's in the second panel. The inner boundary is then updated with this information, and it can be propagated back out to Earth's orbital distance in the third panel. And then the whole region between the sun and the Earth will be updated, and this can then be run forwards to produce a forecast in the fourth panel, which is hopefully better than the previous estimation. So throughout my PhD and my postdoc at the University of Reading, I worked on using BRAVDA to improve solar wind forecasts. I found that using DA improves solar wind forecasts, particularly for lead times of less than 5 days. And this is important for space weather forecasts, as it takes CME approximately 3 to 5 days to propagate from the sun to the Earth. And improving our knowledge of the background solar wind should help to improve CME speed and arrival time estimations at Earth. So enhancing space weather forecasting capabilities can help us to become more resilient to its effects. Improving CME speed and arrival time estimates can lead to a reduced mitigation cost by knowing how severe an event might be and by reducing the amount of times the systems might be shut off for. An increased lead time for events can also lead to more time to put effective mitigation techniques in place. Future space missions will help provide more observations of the space environment. So for example, the Vigil mission is going to be launched at the L5 Lagrange point, which is trailing Earth in its orbit by 60 degrees. And this will provide a side-on view of the Sun-Earth line and will give a good viewpoint of Earth-directed CMEs, as well as offering observations that would be useful for solar wind DA. The Space Weather Instrumentation Measurement Modeling and Risk, or SWIMMER project, is an example of a program that enhances the UK's space weather resilience. So it was a £20 million 4-year project funded by UKRI to develop and deliver key instruments, models and services to the UK space community and to the Met Office. And this is to enhance UK's capability for space weather monitoring and prediction. So more projects like that will help us increase our resilience to space weather. And I think that's about it for me. So.
I'll just stir the mic for a second to open up the floor to questions, and I'll hand it back.
We'll go with Vlad first and work our way up.
Thank you for the presentation. You mentioned the Vigil mission. I know that in ESA, this, Vigil and also in general, the space weather is being a big topic. Is there some kind of collaboration between Met Office and ESA on on mission design or in general on the project on the space weather?
I don't know. Is the most I mean, the Met Office doesn't have capability to develop instrumentation themselves within the space weather part of the Met Office is quite small compared to the rest of it. So we're not like designing instruments or anything like that, but I'm sure they do have the capability and various stakeholders to get involved with projects, and the data will be useful to them. So I don't know whether they are involved, but it wouldn't surprise me if they're not.
Okay, thank you.
Thank you for the presentation. Two questions. First is that you have talked about CME speed, but could you explain what does intensity mean? Like, how do you classify it's bad or not in terms of space weather?
Generally, the faster they are, the worse they are, but also the direction of the CME's magnetic field compared to the Earth's magnetic field has an impact on how severe they can be. So if the vertical component of the CME's magnetic field is the opposite direction to Earth's, we get something called magnetic reconnection, and this can help to accelerate particles into the Earth system, which adds more energy and therefore leads to more severe impacts.
Thank you. And there was an announcement that there was a new space weather model that was released by the Met Office like a couple of weeks ago. Is this in any way related to this work?
Do you know what it was called?
I will look it up, I guess. I'll talk to you after this.
Okay, yeah.
Thank you for that. That was really interesting. So in terms of the forecasting accuracy for the CMEs, do you see this change during the solar cycle? So at like a solar maximum, does the accuracy like increase or decrease or just stay about the same?
Not that I'm aware of. Our forecasting of CMEs is inadequate at best. We have issues with input parameters into the model, kind of rubbish in, rubbish out. But yeah, I'm not sure if there's any dependence on the solar cycle and how accurate our forecasting is of them. But new missions such as Vigil will hopefully help to improve.
Any online? Anna? No. Okay, I'll just come around the bottom. Hi. I know you mentioned that they can sort of shut off sections of the grid to protect them in the event of a sort of solar weather event. I wondered if you have any, like if there's a specific infrastructure for that, you have any communication with the grid, like a sort of early warning system?
I mean, the Met Office will have industrial clients and the power grid is one of them. That's not really on the side that I work in. Yeah, I can't really add much more to that.
Thanks.
Hi, you mentioned the improvements in the forecast for the 5-day period. How does it change with a more extensive time period in terms of performance?
I'll just go back to that plot. Yeah, so you can see this plot just shows an example of a forecast before data assimilation, which is the red line, and after data assimilation in the black line, and the error is up the side. So for all lead times, the DA is performing much better, but particularly that 0 to 5 day lead time is even better than better.
Thank you.
Thank you. You mentioned the period of increased solar activity in May last year. I was just wondering, were you able to predict that with this model, and also how does that compare in magnitude to, was it a very large one? And do we expect anything like that again soon?
Yeah, so I haven't looked at it with the DA, I think as a whole, that event was actually forecast quite well. So I don't know how much the DA could improve that. That event was classified as the highest level of geomagnetic storm, but for that category, it was quite low. So it could be a lot worse, basically. I think there's been a lot of science communications issues around this event because a lot of people or industries have been like, well, if that was the worst category of storm and it didn't really do much because, yeah, we got brighter aurora, but there weren't that many sort of aviation, power grid, spacecraft issues. So communicating across that it could be a lot worse, I think is quite important. And that event, although pretty, it didn't help.
Brilliant. Thank you very much.
We'll take one more. Yep, we'll go again.
How much of the modeling is like on the fly versus just looking at like the stellar activity cycle and mapping solar wind to that?
I'm not quite sure how to answer that.
Like you mentioned that you've got like a satellite orbiting Earth, and then you feed data from that with like the solar wind speed into the model to trace where the solar wind or how the solar wind might affect things.
Yeah.
How does the stellar activity cycle sort of tie back into that?
As in sort of like climatological forecasting.
Yeah.
The climatological forecasting isn't great. Like it's sort of finger in the wind kind of thing. Like people can try and predict solar cycles and see how bad it might be, but yeah, it's not all that accurate. So all of the forecasting is pretty much as it comes, rather than saying like in 3-5 years time it's going to be bad. Like it might be a bit worse, but I guess it's a bit like the Met Office's seasonal predictions. They'll be like, there's a 50% chance it might be a bit warmer. Like, I guess it's a bit like that.
Thank you very much.
Okay.
I think that's all the time we have for questions for this session. Thank you very much again, Harriet. And maybe one last kind of applause for all of our speakers.